Now this one's tougher. I don't know if anyone knows what it is off the top of their heads. Should I just tell you? Well, okay, so again, assuming if x is AB, it turns out we can track this other thing, let's call it y, which is just going to be a over a squared plus b squared, and then minus b over a squared plus b squared. So now let's see what happens when you do x times y. So we know that since x is not 0, at least one of these is not 0, so the denominator is not 0. So this makes sense. So what's x times y? Well, gosh. Okay, it's going to be a times a minus b times minus b. So it's going to be a squared plus b squared over a squared plus b squared. Yep. And then the other term, it's going to be a times minus b over this stuff plus b times minus, or b times a over this stuff, so they're going to cancel. You see that this plus this is 0? So this is going to be 0. So this is in fact 1, 0, which is the one I defined before. Ah, look, we have inverses. And then I checked this, and I mean, I only checked 5 of them. If you were really going to do this, you should have done it for addition, but addition is kind of obvious because I said it was a vector space already. And then distributive properties is sort of straightforward as well. You just have to do another horrible computation like that. But you got to check like x dot y plus z equals xy plus xz. But it's just another horrible computation where you do this thing and say, look, they're equal. Does that make sense? But great, it's a field. Great. I'm sure you guys saw it coming though. So the reason we did, so this is the philosophy behind it. Why did I, so this is actually what we're going to call the complex field. Yeah.
Does that include quaternions?
No, quaternions are not a field. Quaternions are a division rule, but they're not a field. They're a generalization of C. But you can do physics in the quaternions. There's a reason that you can't, but it doesn't matter. But yeah, so definition. R2 with this multiplication is called the complex numbers. And we're going to, I mean, you've seen it before, but we're going to use C to define it. And if you guys are like wondering, wait, that doesn't look like the complex numbers we saw before. If you let the complex numbers we saw before, this be this, you'll see it is exactly the same. Right, so we think of AB as being, and right in the reals, AB being just, 1, 0, or A times 1, 0 plus B times 0, 1. This actually behaves exactly like A plus BI. Does that make sense? This is A plus BI. And so the reason we present it this way is that, like, you shouldn't be thinking that the complex numbers are just like, oh, add the square root of -1. You should be thinking this is a physical object that actually exists, and we're just going to give it this name, and it happens to behave like it's the square root of -1. Like this 0, 1 behaves like it's the square root of -1, or 1 of them. Does that make sense? And that's sort of the idea, and that's why we present it this way. Great. So what did I forget? Oh, this is great. So the point is, the other thing you should realize is in the multiplication that I've erased, if I have no second terms, like I said before, there's no cross terms. Right? The second terms create cross terms. So if I have just A0 and B0, it acts exactly like the reals. So there is a copy of the reals inside C. And that's, I mean, we all know this. I'm just saying, here's a rigorous step in presentation. So for the rest of the class, I'm just going to write A plus BI. So we're going to go back to the usual notation. I just wanted to show you it exists. Fun fact, R2 is the only RK that can be turned into a field. There's no other multiplication you can give to any other vector space that turns it into a field over R. Over Q you can, but we're not talking about that. You can actually make R over Q somehow. It's kind of a mess. But yeah, don't worry about how to prove that R2 is the only one that can be done. If you ever take Math 114, Galois theory, you basically understand why. It'll tell you why. Okay, some notation. So from now on, I'm going to use Z to be my variable. Z is going to be in C. So Z looks like A plus BI. So here's some notation you should know. If I write Z bar, the complex conjugate, I really just mean A minus BI. The other thing you should know is that we often write the real part of Z. This is just A, and this is the real part of Z. And very similarly, we write the imaginary part of Z. I really hate this. Is the imaginary part. Okay, and you guys have seen this, just giving you the notation. So if I ever write this with this, that's what it means. Okay, so let's prove a couple things, or let's prove a couple quick things. Then I'll prove Cauchy-Schwarz and we call it a day. Maybe look at the worksheet. Simple properties. I'm not going to prove all these. I'm just going to state them. But okay, so first thing you got to know, this complex conjugate. Oh, by the way, this is on your homework. There's a question where you need to think about the complex conjugate. I'm not going to tell you where, but it's on your homework. But the thing you should realize, it's super nice. And here's a couple of reasons why it's super nice. And I'm not going to prove these. These are very easy to prove. But let's say let Z and W be elements of C. Oh yeah. If you ever take complex analysis, you'll see this. Z and W usually are used for complex variables. X and Y are used for real variables. I didn't make the rules. I'm just learning it that way. But anyway, Z plus W conjugate is equal to Z conjugate plus W conjugate. Z times W conjugate is going to be equal to Z conjugate times W conjugate. And then some nice little identities. If you want, I can prove these two, or maybe I'll just prove one of them. But if you ever add Z to its own conjugate, what do you get? Does anybody know?
Twice the real.
It's twice the real part of Z. It's really easy to see. Just think about it. Add this to this. What are you going to get? 2A. Not that surprising. D. What happens if you subtract the conjugate? What do you get?
Twice the imaginary.
Almost. Do it. What happens? What am I missing there? The I. It's 2I. Just keep that in mind. This always messes people up. But it's 2I, the imaginary part of Z. And the only reason we care about this is I won't come up too much because we're not doing too much with complex variables in this class. But like sometimes instead of writing the real part, I'll just write like Z plus Z over 2. Z plus Z bar over 2. And it just simplifies writing stuff sometimes. Especially if you have a lot of variables running around. But yeah, just keep in mind, don't mess this up. The imaginary part of Z does not have an I. It's the real part. It's a real number that multiplies by the I. Just keep that in mind. And then the last thing I wanted to say is Z times Z bar is an R, and Z times Z bar is greater than 0 if Z is not 0. You guys knew this? Well, I'm only going to prove E. The others are pretty straightforward. I mean, you guys can do it on your own, I think. But for proof of E, Z times Z bar, well, this is just A plus BI and A minus BI, which is just equal to A squared plus B squared. So that's clearly going to be greater than 0 if A and B, if one of A and B are not 0. The only way it's going to be 0, it's going to be if both are 0. Does that make sense? And just so you know, we write this. Z times Z bar is equal to the absolute value of Z squared. For any complex number. That includes a real number. Right? Because if you have a real number, this just looks like, well, itself squared. Right? Very easy. I know this is the last bit of like easy stuff we'll probably do in this class. Then we'll do some new stuff. Okay, so yeah, we define this to be the square of the absolute value to be Z times Z bar. And the only reason that matters is, again, we won't come up too much in this class, but there's a lot of times where you actually want to write concretely write this function down into something you can manipulate, right? Because it's always scary to work with absolute values, because you can't just you have to be careful when you use absolute values. But anyways, so some properties of this absolute value. So definition. This is my definition for the absolute value of Z. So some properties of this guy is just, and you guys already saw this. Z is greater than 0. Z bar and Z have the same absolute value. Z times W, the absolute value of these guys, I can prove this if you really want, is the same as the absolute value Z times the absolute value of W. What's the other one I wanted? Oh, C, so D next. The real part of Z, and same thing, the imaginary part of Z, has a smaller